I forgot about the meeting today, so the meeting is now on YouTube. So I'm just going to briefly go through the example of Minuit fits that I wanted to show. So, brief presentation. So what this is a brief introduction to Minuit2 intended for particle physics analysis students who want to get something working very quickly and not spend a long time reading a lot of documentation or searching for an example online. I just produced this quickly one evening. There could be many bugs lurking. Don't use this as a de facto standard. What this is not a guide to best practices. This is not a detailed overview of all the technicalities and nuances relating to obtaining correct minima or verification of results from Minuit, of which if you do a lot of fitting you will learn many things about. This is not an in-depth guide to all of Minuit2 functionality. So what we will do, we have example.c. We will find the minimum value of x square. There are no prizes, especially no Nobel prizes, for guessing the answer in advance. We will then find the minimum value of x square with a Gaussian constraint. So example2.c, we have two example files. We will create some fake data using trandom3, and we will scale this data, and from this scaled data we shall create a new fake dataset. We will then use Minuit2 to find the scaling coefficients that have been used in a mock parameter fit, which will be much more applicable to something that's closer to what you will really be doing. And here is where you can download the examples. So with that out of the way, let us proceed. So let's load example.c. We could just open this as well with Vim and have a look. I won't go through this in detail. There is a main function called example, but there are two main functions really. There's the example with no constraint and example with a constraint. So let's just run them and see what happens. So a load of stuff was printed on the screen. Let's scroll back and have a look. So the output you're seeing here is the output from the minimization class. So the way Minuit works is you have a class, I've called mine minimize FCN, you can call it whatever you like. It has to inherit from root Minuit2 FCN base. That's the base class for any class that should interface with Minuit2. It has to inherit publicly. There's some stuff in here called errordef. The only thing you need to know about this is you set it to 1 if you're minimizing a chi-square, or if you are maximizing a log likelihood, you change it to 0.5. This up function just returns that variable, and then most of the real work is done in this operator here, this bracket operator. It takes as arguments a list of parameters which you define outside of the class. And the way this works in this example is very simple. We calculate this variable called fval, that's what we return, it's the function value, it's the thing that in this case we wish to minimize. And all we do is we say that x takes the value of parameter 0, and we square x and add that to fval. And if we're doing things with constraints, then we add a constraint, but you could ignore that for now. And there's some debugging output. And from this we see that the first function call was done with the value 3, and the operator returned 9, which is 3 times 3. And then a few more things happened, and Minuit tried 3.005, it tried 2.995, and a few other values, and then eventually it went all the way in one big jump to something very close to 0, and it moved around a little bit, and it finally satisfied itself with a value that was down at 10 to the minus 10. Basically, it's 0 within the precision that Minuit is going to minimize to, which you can change, but I've not shown that in this example. So it then summarizes and says param 0 was changed from 3 plus or minus 5, so it had that as the initial uncertainty, to 9.9 times 10 to the minus 11 plus or minus 1. Now what the plus or minus 1 means is that is the 1 sigma band in this case, and that is the importance, that is why it's important to set the error def variable correctly. And this is indeed correct. We know the minimum of x square is 0, and the 1 sigma band, i.e. our chi-square, must change. We must have a delta chi-square of 1 when x goes up to 1, because 1 squared is 1, or down to minus 1. Minus 1 squared is also 1, so either if you go plus or minus 1 from 0, you end up with a delta chi-square of 1, which is the definition of a 1 sigma error band. So done. It was easy. Good. Finished. The next example then executes immediately afterwards. In this case, we've enabled a Gaussian constraint. Let me just run you through how that was done. So in this function, where is it? Ah, yes, here we go. So that's defining the parameter there. Parameter number 0 starts off at 3 plus or minus 5, and then, yes, here we are. So I have a variable inside my minimization class called constraint enabled, and I just set it to true in this case. How did I put the constraint value in manually here, but you could obviously provide get and set methods to change that. If you're wondering why everything's mutable here, it's because I believe I'm correct. I just copied this from a previous code that I had. So assuming I wasn't wrong previously, you have to define this operator as const, which means that if you want to mutate any variables in this function, in this class with that function call, then you have to make things explicitly mutable. And there's a long discussion here about the philosophy behind that. It's possible that I'm wrong and that const is not required, but I think I'm correct in saying that it is. So yes, that's all very good. So the constraint value, it has a central value of 5 and an uncertainty of 1, and I detail somewhere as to what the expected result would be, and it is not here. Where are we? Here it is. Yes, so I calculate what the expected result would be, and the expected result should be, you should minimize this function when x has a value of 2.5, because a Gaussian constraint is just of this form. It's making me wonder why it's called a Gaussian constraint, actually, considering that this is a quadratic thing. I don't know why it's not called a quadratic constraint, but anyway, that's an aside. Going back to the output of this, we see that Minuit started with a value of 3, in which case the output is 9, and the constraint, the value of the constraint was 4. So 9 plus 4 gives you a total, assuming you're pretending this is a chi-square here, so a total of 13, and there were a load more function calls, and eventually Minuit satisfied itself with a value of 2.5 for x, in which case the total from fval is 12.5. So fval changed from 13 to 12.5, and this gives you how the parameters changed. So the final value has a central value of 2.5 and an uncertainty of 0.707. So good, that's the first example done, and hopefully it's fairly easy to follow through what this code does. So here we just initialize some things that we will require to do the minimization. There's different ways of different algorithms for doing this. I just chose that one. I then add to the parameter state an initial parameter. All the parameters have to have a name. I don't know why that is, but that's just how Minuit works. I convert those parameters into vectors and figure out the value of fval before minimizing anything just by calling that operator. Set the minimization strategy, not a clue what that does to be honest with you, and then find the minimum. Like I say, brief introduction, not in much detail. And then here I show how you can get the parameters back from Minuit and how you can find fval after, though of course you'll already know that because it was the last function call made, but this is if you want to write these values to a file or something for debugging, useful. Good. So now let's have a look at example 2. It's largely the same. If you go up to the top, you'll see that there's still this class minimize FCN. It does mostly the same stuff, except for this time you have an init function, you feed it some th1s to use as data and Monte Carlo. So you have to imagine here there's data we're going to construct later it's some pretend fake data as if that came from your experiment, and then MC1, 2 and 3 are like background channels. So blah blah blah, here's the operator function. Basically what it does is it goes bin by bin and it adds up the content from all the backgrounds MCs, and it has parameters A, B and C, which are just param 0, 1, 2. They're set here, and it checks what the total is, this total sum here, against the data that it has, and essentially it uses the square root on the Monte Carlo as the uncertainty, and it just does quadratic errors and adds them up in a loop and returns the value as fval. So yes, it's a one-dimensional histogram fit. And the best thing to do with this is really just to demo. So let's load it up, because you're going to see what it does. There, I think it's called example. Yes, it is. Good. So it produces two figures. This is the before fit histogram figure thing. This is the one that's after. So you have three background channels. They're in different colors. I've just stacked the histograms. You've got one thing that is a kind of peaky Gaussian. You have something that's a very flat Gaussian, and then an exponential background. All I've done is given these three a certain scaling and added them together to create some fake data, which are the black points. And then I have instructed Minuit to minimize the background MC difference using 3 parameters. And what does it do? So the final call to operator, I should have updated this line actually, but never mind. The final call to operator had a value of 3, roughly 2 and 1. So let's see if those were the values that I used in my scaling. A coefficient was 3, B coefficient was 2, and C coefficient was 1. So indeed, Minuit does find the minimum, and it's able to figure out what those parameters are. I can very quickly make a small edit to this code by adding in here a couple more lines so we can see what the errors were. Just bear with me one moment while I edit this on the fly. Oops. I can't see my keyboard because the microphone's in the way. So that should work. So I should be able to rerun the example. Okay. So it now gives us uncertainties on the parameters as well. So parameter A is 3 plus or minus 0.07-ish. Parameter B, 2 plus or minus 0.06-ish. Parameter C, 1 plus or minus 0.04. So if you change any one of those parameters by the uncertainty given here, then you will get a delta chi-square of 1. I think that's how it works. We could test it. Or we're going down a rabbit hole now. Yes, let's do this. Whoops, 0. So let's add on. Is it param errors? After, I believe. So we'll add on the error to that one, and let's do another function call. So we can do this. Put this here. I'll call it fval after 2. And then let's just see out this. Another one. Oops. This should work. Oh, how have I done that? I pressed F1. Don't want to do that. Does it work? So it changed from 5 times 10 to the minus 6 to 1.14 times 10. Okay, interesting. That's a bit more than 1. That's not what I would have expected to see here. I wonder why that's happened. Possibly because it's a multiple parameter fit. So if I remember my statistics correctly, the delta, the 1 sigma band, I don't remember exactly. We could ask the collaboration. Somebody can tell me why this happens. Why has it done this? Why is this not closer to 1? Considering that this is so close to 0. Somebody else can tell me that. I don't know. Maybe my hunch is correct. You let me know. Anyway, that's it. That concludes the end of my presentation. So hopefully this was helpful if you've been told to do an analysis using Minuit. Don't use the old Minuit, use Minuit2. Yes, thank you for listening.